all. So here we are for the last unit of Chem 111, Chem 112 General Chemistry course. So this unit is the Descriptive Inorganic Chemistry course, and it's going to be about four lectures. So, oops, let me get us started. So the assignments for this chapter used to be 10 virtual chemistry lab assignments. Because half the class doesn't have access to virtual chem lab, we have replaced those with some book problems. And the sapling still exists, but then the homework problems that used to be online have been replaced. So those will be uploaded to Learning Suite by the time you guys are working on them. Of course, right now, many of you are working on studying for as I'm recording this, exam 3, and also getting caught up on nuclear decay. So by the time you read this, we'll have that up and going. So the overview for this section is to predict reactivity for many elements in the periodic table, to be able to understand and rationalize exceptions in the periodic table, and then also to identify select chemical reactions for different periodic table groups. So that's kind of the general overview. I just wanted to double check that I was recording. So back here, this is just gonna start the unit off with the periodic table, and I'm gonna do a few of these lectures, as well as Dr. Paxman is gonna do a few of these lectures, and then you guys can, of course, continue to ask us questions during virtual office hours, virtual class. So the first thing we're going to talk about is what are some reliable patterns in the periodic table. And why I say reliable, because so many of the patterns in the periodic table, students want to say that all of the families or everything in that group is the same, and that ends up not being true. So one of the first very reliable trends is the alkali metals, which is group 1. And these have a decrease in melting and boiling point as you go down the periodic table. So from lithium and sodium all the way down to the bottom, which I can't remember what that chemical is right now. Let me grab a book so that as I talk about this, we can actually use things. So from lithium down to cesium, I won't really talk about francium since it's nuclear. It decays. So the decrease in melting and boiling point as you go down, meaning it gets easier to melt and boil these metals as you go down the periodic table. And so why would that be the case? Well, that's the trend of the size. As you go from the top of the alkali metal group down to the bottom, you're increasing the size, you're increasing the molecular weight, and therefore you're increasing the strength of the intermolecular forces. And so that's a really nice reactivity increase down the group. So I'm going to show you this video. Whoa. Here with this really awesome so that's cutting through a metal, so it's pretty soft. Oxides. So right here, and that's lithium oxide. You can cut it with a knife. Okay, so here's adding them into water. Terrifying. Okay, so again, as things are reacting down the periodic table, you end up with reactivity increasing, and that's because they're more reactive as you go down the group. So then the only tricky part in thinking about oxides and what oxides are formed is that lithium is the only one that forms a normal oxide. So the lithium 2 oxide is what forms, but all the other ones will actually form peroxides and superoxides. So this is where you have, so like K2O2 minus would be potassium peroxide, where you've got each of those oxygens have a -1 charge. Similar to how we saw mercury 2 plus, each mercury atom has a +1 charge. And so all of the everything, sodium, potassium, rubidium, cesium, these all form peroxides and superoxides, where the lithium oxide forms a normal oxide. Another reliable pattern of the periodic table is the halogens. So trends with size, again, you're going to increase in your melting and boiling points as you go down the table. And so in this case, you actually have stronger intermolecular forces. Your increase in melting and boiling points because they are going to take longer to come together. So your reactivity decreases down the group, where you have hydrogen reacting with a halide goes to 2 moles of hydrogen halide gas. So let me just make sure. This says it increases in melting and boiling points as you go down, because you're increasing the stronger intermolecular forces. So that's what I said was true with this one. But then this, you're decreasing in your melting and boiling points as you go down the periodic table, because you actually have weaker metallic bonding. Sorry. So so let's review the difference between alkali metals and halogens. So alkali metals, you are increasing your size as you're going down, but you're decreasing your melting and boiling point because all of your alkali metals have metallic bonding, and metallic bonding is kind of like that band structure of molecular orbitals that get combined together. And as you combine molecular orbitals, the ones that have a lot of charge density are going to be up at the top of the family. The ones at the bottom are going to have those more diffuse molecular orbitals. And so the electrons are held less tightly within that metallic bonding as you go down the group for the alkali metals. For halogens, as you go down the group, you're increasing the molecular weight, therefore you're increasing the strength of the intermolecular forces. And so your melting and boiling points are going to increase, as opposed to the alkali metals, they're going to decrease. So this is why your alkali metals actually have an increase in reactivity as you go down the group, because that metallic bonding is much less strong, and therefore they're more likely to form oxides and peroxides and react with air, because the bonds are more reactive because they're weaker, as opposed to with the halogens, your strongest reactivity is going to be at the top of the group, because this is where you have weaker intermolecular forces and bonds. And we're going to talk about that a little bit more. Finally, the noble gases, which are just used as inert gases, with the only exception being xenon. So most of these don't actually do anything. They're just inert gases. So the only other very reliable trend is that the first element of every group will have exceptional reactivity to the rest of the group. So one other word that we use for groups is congeners, or congeners. I'm not really sure how to say that word, but C-O-G-E-N-E-R-S. You've seen it in your book. So what this means is that, you know, all of the families, they have a similar valence, they should have similar properties, but that first element of all of the families behaves a little bit differently. So carbon is going to behave differently from the family. Lithium behaves a little bit differently than all of the alkali metals. Fluorine is very different from all the other halides. And so this is the only other very reliable trend. So as part of this class, we're talking about descriptive inorganic chemistry. And so what is inorganic chemistry? What is an inorganic compound? So an inorganic compound is one in which is made up primarily of non-carbon, oxygen, hydrogen, and nitrogen bonds in the way that organic compounds form. So all of organic compounds are what we have in our bodies, in a lot of structures where you have carbon, nitrogen, carbon, hydrogen, carbon, oxygen bonds. So one inorganic compound that would be pretty difficult to classify would be something like carbon dioxide or carbon monoxide, because technically this is an inorganic compound, because it's not it's not bound to carbon hydrogen. It doesn't have like carbon hydrogen bonds in it, but it is organic because it's carbon and oxygen. So that would be kind of a bad example to give you on an exam. Something like ammonia could be an organic compound because we use it in a lot of organic reactions. It's produced in organic reactions, but it could also be considered inorganic because we make it from elemental compounds of nitrogen gas and hydrogen gas. So what is an inorganic compound? And an inorganic compound is something that primarily has carbon bound to metals or oxygen bound to metals. It's a combination of metallic and non-metallic bonds that are not carbon and hydrogen based. So examples of that would be oxides, so tin oxide or permanganate ion or nitrate or iodine. So these are all examples of like NO3 minus, MnO4 minus, NO. So nitrous oxide, NO would be a good example. And so those are things that are going to be inorganic compounds. And so if we look at this list, which of the following is not an inorganic compound? So we've got zinc bromide A, chlorine trifluoride B, CH3, CH2, COH, which if you drew that Lewis structure out, it would look like a carbon with hydrogens bound connected to a carbon with hydrogens bound to a carbon that's double bonded to an oxygen with a hydrogen off of it. So that's that aldehyde that many of you might know about, but some of you don't, and that's fine. And then lithium C6, which would be like a lithium carbide. So which of the following is not inorganic? So I would say, I'm going to pause. Okay, I would say that the zinc bromide is inorganic, so you've got a metal and a halide. The chlorine trifluoride is all halides, so that's going to be inorganic. The CH3, CH2, COH is a dead giveaway that that's organic because you have carbon-hydrogen bonding all through there. So carbon-hydrogen bonding is a pretty telltale instance of an inorganic compound. I threw the lithium carbide in there to throw you off because I wanted you to realize that just because you see carbon doesn't necessarily mean that it's an inorganic compound. So the answer here is doesn't necessarily mean that it's organic. So the lithium carbide is going to be inorganic. So again, the answer here is going to be C. Okay, so let's talk about why there are such large differences in trends on the periodic table, because it's grouped so nicely. Why would we try to talk about trends if there really aren't very good consistent trends? So so in this periodic table, as we go from left to right, your homoatomic bonding is going to change from metallic to covalent. So if we think about the two families that we talked about, the alkali metals here and the halides over here, the alkali metals are all metallic bonding, right? And we get metallic bonding all through here, through here, through here, and then through here, you have some metal-like bonding and some covalent-like bonding. And then as you get to this part of the periodic table, these are your non-metals where you're going to get covalent bonding. So all of the halides have covalent bonding. All of the alkali metals and alkaline earth metals have metallic bonding, and that's why you see the difference in the trends as you go from top to bottom. These are becoming more reactive, so the bonding is becoming weaker as you go from top to bottom. This is covalent bonding, so from top to bottom, my covalent intermolecular forces are increasing. The covalent bonds between themselves are the same, but the intermolecular forces are increasing, and therefore they're becoming less reactive as you go down. And so that's the major difference from there. So for example, if I think about lithium, the melting point of lithium metal is 180 degrees Celsius. The melting point of carbon, so like a carbon graphite surface or a carbon diamond surface, is going to be 4100. So that's carbon in its form that's more like networked. It looks more like a lattice than any sort of covalent bonding. And then as we go to oxygen, its boiling point, its melting point is negative 229 Celsius, right? So it's like pretty much a gas. If we look at another set of examples, here's sodium, so 98 degrees Celsius is its melting point, and again, again, it's a lower melting point than lithium because you have decreased metallic bonding. Silicon is 1,420 degrees Celsius, and so this is again, you have that networked silicon bonding, which is a kind of metalloid type network. And then you've got S8, which is a pure form of elemental sulfur, and that's now 119, so we've gotten a lot weaker. And then chlorine gas, negative 101. So then as you go across the periodic table, you've got bonding changing from ionic to covalent. And so if I take any of these metals and I combine them with any of these nonmetals, I'm typically going to get ionic bonding between metals and nonmetals. And then if I go from and even if I go from, you know, a metal to a metal, I'm still going to have metallic bonding between the two metals. And then if I combine any of the nonmetals with each other, I'm going to have covalent bonding now. So if I look at lithium fluoride versus boron trifluoride and carbon tetrafluoride, this bonding is going to be considered ionic. The BF3 is considered is kind of like on the borderline of covalent, and then CF3 is definitely covalent. Lithium 2 oxide, so here's that lithium oxide that we talked about, again, is ionic. The boron oxide is going to be like on the borderline between ionic and covalent, and then CO2 is definitely covalent. And so then if we look at the next series, magnesium oxide, definitely ionic. Silicon actually has some specifics of covalent and ionic characters, so it's considered more of a covalent oxide. And then phosphorus oxide is definitely covalent. And so that's kind of the differences as you go across the periodic table from the metals to the nonmetals. Okay, so let's talk about weird trends that we don't usually talk about. So these are the trends where we've got N and the N plus 10. So if you've ever looked at a periodic table, what you see is 3B and 3A, and 4B and 4A, and 5B and 5A, or 5 and 15, 4 and 14, 3 and 13. And so usually we don't really talk about these trends, but what is true is that there's often similarities in chemical reactivity between group N and group N plus 10 in one or more cases. So let's look at aluminum and let's look at scandium. So if we look at aluminum and we look at scandium, again, we're not going to look at boron because that's the first in the family, so it's going to be a little bit weird. But if you look at aluminum and scandium, those both are going to have similar chemical reactivity, mostly based on a similar electron configuration. So for group 3, if I lose 3 electrons, I'm going to have a neon electron configuration, and for scandium, if I lose 3 electrons, I have an argon electron configuration. And so the aluminum and scandium sizes are pretty similar, the charges are similar, the charge density is similar, and so in those cases you have similar reactivity. So let's look at another one. So here's titania and silica. So here's titanium and silicon. So again, you have similar numbers of electrons that can be lost. So here's a unit cell structure for titanium oxide, titanium 4 oxide, and you can kind of see that rutile structure where you've got a coordination number of 6 between the titanium on the inside, and then you've kind of got these different holes that are filled in this face-centered cubic oxide structure here. And then for the tin oxide, again, it's a slightly different orientation, but here's your hexacoordinated tin in the middle, and then that same like face-centered cubic oxide structure where you've got the holes filled here. And so those have the same structure, they have the same behavior in water. There's also similarities between tin and silicon. So titanium and silicon, as well as titanium and tin. So this is the titanium tin example here. So those are going to have somewhat similar ideas. Zirconium also forms a similar oxide. So the next one we're going to look at is vanadium and phosphorus. So vanadium and phosphorus, they form the same ion. So if you look at these, here's vanadium, here's phosphorus, same tetrahedral oxoanions in the same 5+ oxidation states. And these are strong bases. So these are both strong bases. They have similar speciation trends in water in terms of how they react and collect protons. So the next one we're going to look at is chromium and sulfur. So again, if you think about these, you can think about forming those strong oxo acids in the +6 oxidation state. Sulfurous acid and chromic acid are both considered very strong acids. And then the +5 oxidation state isn't quite as strong. Finally, you've got your manganese, and chlorine. So those also form strongly oxidizing oxo anions. So here's your redox couple for manganese 7 plus going to manganese 2 plus, and that's 1.51. For chlorate going to chlorite, the redox couple is 1.23. So these are strongly oxidizing anions in their highest oxidation state. And then we've got osmium and xenon. So xenon is the weird noble gas, and if you put osmium and xenon both in the highest oxidation state, they tend to be explosive in terms of their reactivity, their chemical reactivity. Okay, so again, interesting trends where you've got your 3B and your 3A complementary reactivity, and it's not a trend that's often discussed, but it is a trend that kind of makes sense when you think about valence electrons and valence states in terms of how many that they're losing. Their valence electronic configuration looks very similar in similar oxidation states, and so you can imagine that they would have similar reactivity. So another relationship that we talk about is diagonal relationships. So this is an element and that to the lower right. So if I think about lithium and magnesium, they both form a normal oxide. They both form nitrides, and they have similar insolubility to alkaline earth or alkaline earth metals. Is the lithium has similar insolubility there. They both have somewhat covalency in bonding. So what that means is that if I wanted to make a lithium carbon bond or a magnesium carbon bond, I could, but I can't make a sodium carbon bond, and I can't make a calcium carbon bond. It's just these two that have like really good covalency similarities in bonding, and they're similarly sized. So one of the nice things about these diagonal relationships is people have thought about trying to substitute in magnesium for lithium batteries, because magnesium has this very similar size and similar properties as the lithium. And so in terms of that reactivity, magnesium would be nicer because it would have a higher charge density. But in terms of the ways they decompose, it hasn't quite been figured out. But I can imagine not too many years in the future being able to have magnesium batteries that are very, very competitive with lithium batteries. So the next one we're going to talk about is beryllium and aluminum. So beryllium and aluminum have a similar charge density. They have a similar oxide overlayer formation. They form carbides in similar ways. The reason we don't have so many beryllium applications is that it's really not as abundant as aluminum, but they do have similar reactivity. And then boron and silicon are going to form similar oxides. They're going to have oxides that have similar properties. They're both acidic. They're both polymeric in the forms that they have. So let's talk about these elements down here. So these are elements that have lower oxidation states than expected from the group number. And so you would expect that indium and thallium, its most normal oxidation state would be 3+, because that's what we see for aluminum and gallium, right? Aluminum 3+, gallium 3+, indium 3+, thallium 3+. But the problem is that the indium and thallium actually prefer to take a +1 oxidation state. The tin and lead compared to silicon 4+, germanium 4+, tin 2+, lead 2+. If we think about nitrogen and phosphorus, we think about those taking like a 5+ form, but antimony 3+, bismuth 3+. And so in terms of these lower oxidation states that are expected from the group number, the issue is that there's a higher ionization effect because you have the lanthanide contraction. All of these f orbitals that show up before we get to indium and thallium and so on are so diffuse that the electrons aren't shielded, and so therefore it has a higher ionization energy to remove those electrons, which leads to not removing the electrons entirely, and so you just remove the one in the p shell instead of removing them all the way down to the s shell. And so that's what's known as the inert pair effect, is that you tend to have lower oxidation states in metals following the f orbitals, because those f orbitals aren't shielding enough, and therefore electrons are harder to remove. And so they have a higher ionization energy, leading to stabilizing of lower oxidation states. Okay, so in general, exceptions to these other trends can be reasoned through electron configuration or charge density arguments. So first, let's talk about hydrogen. So I have named hydrogen an element without a family because hydrogen often is found on top of the alkali metals, or it's often found on top of the halides. Those are the two groups where it often resides. However, it has similar electronegativity to carbon, and carbon is its most often bonded partner. So if you think about hydrogen, it essentially could take 3 spots on the periodic table: above the alkali metals, above the halides, or above carbon. And so in thinking about hydrogen, the reactions that typically occur is that hydrogen gas will react with oxygen to form water. Hydrogen gas will react with fluorine to form hydrogen fluoride, acid, HF, hydrofluoric acid. Hydrogen will react with nitrogen to form ammonia. Hydrogen will react with copper oxide to reduce the copper to copper metal, to reduce the copper oxide to copper metal. And so reductions essentially are happening everywhere. Hydrogen is a great reductant. It is going to be reduced very easily to form the H+, right? So the synthesis of hydrogen is pretty important. You can either take zinc and react it with hydrochloric acid to make the zinc chloride and release hydrogen. And this is, could be fine, except that we don't want to take all of our zinc and replace it with and make it into zinc chloride. So the other way that it's done is we take methane gas or natural gas and water, and we do a steam reforming process. So where these two things are combined together, so that the methane is oxidized to carbon monoxide and the water is reduced to hydrogen gas. And this is done over a nickel catalyst at 500 degrees Celsius. And that's the most large-scale pattern for producing hydrogen gas. Other patterns that we're really interested in are electrolysis, right? So being able to take water and split it up into hydrogen and oxygen. So a lot of people are working on the electrolysis of water to be able to get that to happen. So hydrogen reacts with metals to form hydrides, and it reacts with nonmetals to form covalent hydrides, right? So you can form either one. And so if you have a metallic versus a covalent hydride, a metallic hydride is where you'll have the metal in the plus charge and the hydrogen in the minus charge, as opposed to like methane, which is going to be covalently bonded. So you have silanes, you have phosphanes, you have palladium hydrides, etc. Can you give your own examples? Can you figure out what your hydride formula would be? Let's say if I gave you an element and I said phosphorus, tell me what the hydride would be if you were to form phosphorus hydride. And so you would say, okay, it would be pH 5. Okay, that's fine. What would be the formed hydride if hydrogen reacted with, let's say, aluminum? Well, aluminum has a 3+ charge, and so I'd have AlH3. That would be my aluminum hydride. So that's pretty straightforward in terms of thinking through that. If you had bromine that reacted with hydrogen, what would you form? You'd form HBr, etc. So those are how you're kind of thinking about how hydrides are forming. Okay, so so to recap on this slide, what arguments can be given for belonging or not belonging to each group? Well, in terms of hydrogen reacting like an alkali metal, it's very reducing. It's the reducing agent. It's easily oxidized, similar to how all of group 1 alkali metals are easily oxidized into the +1 state, right? And then in terms of halides, it also reacts as a halide because it's readily available to form that hydride and accept that electron to then form the helium noble gas configuration, right? So that's how it would belong to group 1 and how it would belong to group 17. But in terms of why it doesn't belong to each group is that that's not always the reactivity that it has. It often has one reactivity in one case and one reactivity in the other case. And so then what's the major difference between ionic and covalent hydrides in terms of physical properties? So the major difference is that ionic hydrides are going to have metallic bonding. They're going to be brittle. They're going to have high boiling points, high melting points. It's going to take a lot of energy to break up a solid into a liquid or break up a liquid into a gas. In terms of a covalent hydride, those are typically covalent anyway. And so if it's small, it's already going to be a gas. If it's larger, it's going to have larger intermolecular forces. And so it's going to be have a higher boiling point as you go down in terms of increasing molecular weight. And so physical properties of covalent hydrides is that they tend to be gases, whereas ionic hydrides tend to be solids. Let's talk about group 18. So group 18 also has a well-behaved trend in densities, melting points, boiling points. There's a low abundances, although argon is quite high. So if you need an inert gas, argon is your person. They all kind of are used as an inert gas, and so then they can kind of fluoresce a little bit differently. And then xenon is the only element with known compounds in a family. So the xenon fluorides are strongly fluorinating, meaning that they're going to give up those fluorides to something else. And the xenon oxides are strongly oxidizing, meaning they're going to give up those oxygens to something else to be reduced. And that should make sense because xenon is fine being a noble gas, and so if you put fluorines on it or oxygens on it, they're going to want to give those up and send them off to some other molecule. So we're going to come back to alkali metals. So this is a mostly happy family. I'm going to take out lithium here because it's kind of an exception. So the trends are going to be consistent within this family. The salts are going to be soluble. The metals have characteristic flame test colors. So here's your lithium that's pink, and your sodium that's orange, and your potassium that's purple. Rubidium and cesium are harder to tell because they've got different colors that are very similar to potassium. In terms of all of these metals, they are going to have low densities, low melting points, low boiling points, high chemical reactivity, and then they'll form soluble salts with large anions. There are some exceptions, so this little star asterisk here, for heavier metal ions, so rubidium through cesium will sometimes not have soluble salts because they have more covalent character in the ionic lattice, and so therefore they're harder to solubilize. So then here's some applications worth knowing about. So let's talk about sodium and potassium channels in your body. So in order for all of your cells to have the appropriate osmotic pressure associated with them, so if you remember way back to chapter 5, Unit 5 in Atkins, where we talked about osmotic pressure, you have to have similar ionic concentration on the inside and outside of the cell. So extracellular would be outside, intracellular would be inside. And so in terms of these pumps, most sodium concentration, high sodium concentration is kept on the outside of the cell, and most potassium concentration is kept on the inside of the cell. And so how does the cell do that? Well, the cell does that through these very intricate channels where you have hydrated sodium and potassium ions that go through these channels. And because of the size of the hydration sphere on the sodium and the potassium, you can get the channel to open when it knows that the potassium is in there, and so it will let a potassium through, or it will let the sodium out in terms of how they open and shut. And so it's pretty amazing because you're not really selecting on any chemical reactivity, which I would argue is a little bit easier to select on. In terms of chemical reactions, your body is operating on size selectivity, where again the sodium is being pumped out and the potassium is being pumped in based on just like the size of that Lewis acid, Lewis base hydrated ion. And then a leaky channel would just kind of have no differentiation between the ions that were coming in and out. So the other huge application that many people know about is lithium batteries. And so in this case, you've got your cathode, which is your lithium metal oxide, and then you've got your anode, which is your lithium carbon graphite area. So the lithium is all of these red ions here, and the lithium is exchanged between the cathode and the anode, and it goes back and forth through a porous separator. And so in terms of what's happening, you have your cobalt oxide that reacts with lithium ion to reduce to the cobalt oxide solid. The lithium carbon will be will oxidize that lithium up. So the lithium is then oxidized and goes to the lithium plus, and then that's exchanged across. And so that's kind of a nice application of lithium batteries. Okay, so then where are the sodium ions and potassium ions located with respect to living cells? Is it A, sodium and potassium are both intracellular? B, sodium and potassium are both extracellular? C, sodium is higher intracellular than extracellular and the opposite for potassium? Or D, sodium is higher extracellular than intracellular and the opposite for potassium? So pause. So sodium is higher extracellular, and potassium is higher intracellular. So the answer here is D. So let's talk about the alkaline earth metals and trends with the beryllium on its own. So if you think about alkaline earth metals, these are going to be harder and denser and less reactive than alkali metals. So when we talked about cutting them with a knife, these would be harder than cutting with a knife. They're still a lot more reactive than other metals. They're going to react to form oxides, etc. And so in terms of reacting to form salts, the salts are going to be if they react with -1 charge salts, these are soluble. Maybe they're, I'll have to get back to you on that. It said that if it's -1, they form insoluble salts, so that calcium chloride would be insoluble. Magnesium chloride would be insoluble. I would imagine those would be soluble. So then the sulfates are going to be soluble at the start of the family, and as you go down they're going to become insoluble. So if you think about something like magnesium sulfate versus calcium sulfate, magnesium sulfate would be more soluble than the potassium sulfate, than the calcium sulfate. So as you go down, you're going to be more insoluble as a sulfate. And then the oxides are going to go from insoluble to soluble. So as you go up, the oxides are going to be insoluble to soluble. So we're going to see that on the next slide. So then in terms of burning in air to form oxides, your calcium reacts with oxygen to form calcium oxide. Barium reacts with oxygen to form barium oxide. And then magnesium can also form these oxides, but then also form covalent bonds. So this is what we were talking about in terms of magnesium carbon bonding. And that's kind of very unique to carbon and lithium. And then calcium is the 5th most abundant in the earth. And so we've got limestone that reacts with acids again to kind of under acid rain conditions, you'd kind of have issues with that falling apart. And then cement is calcium with silicon together in kind of this ternary or binary oxide. Gypsum is basically salt, so this is an example of salt. Chalk, so calcium sulfate that's been hydrated. And then hydroxyapatite is that calcium phosphate structure that we get in our teeth and bones. So then let's talk about beryllium. Beryllium has covalent bonding. And so in terms of how it bonds, it has that high charge density because it's really small, which is going to polarize anions, which is going to make it kind of have more metalloid type bonding. So it's going to have covalency to its lattices. So let's talk about the hydroxides again. Yeah, so here's my magnesium hydroxide, which is the most insoluble. And then as I go to barium hydroxide and strontium hydroxide, these are both soluble. But then if I think about my sulfates, my magnesium sulfate is the most soluble. And then you go down to strontium, and that's going to be the most, that'll be insoluble. I'm not sure. Strontium is before barium. So I'm not sure why we've swapped those. So the strontium comes before barium. So then in terms of carbonates, it's a little more mixed. So your magnesium carbonate is the most soluble, and then calcium, barium, strontium. And you can think about that in terms of size. So you've got better size matching between your calcium, barium, and strontium. So some ways to distinguish and separate the cations would be just in terms of your concentration of sulfate that you add in. And so this is example of separations that you would be able to do, just thinking about the sulfate concentrations between barium, strontium, calcium, and magnesium. So I'm gonna let you guys watch this. I don't know if you can actually hear it. You probably can't, I just realized. So in terms of separating these, you can separate them on sulfates or hydroxides or carbonates. There's a 3-order magnitude difference between barium and strontium, and they're quite less soluble than the calcium. So then he's pointing out here that you can change sulfate concentration through different acidities in solution. So if you make it super acidic, then once you add the sulfate, that's going to give you the lowest amount of sulfate ion concentration, and therefore your barium sulfate will participate out. If you raise the pH or you change the pH, then you have a little bit more sulfate that is in there. So then to separate out these two, one of these is going to be a hydroxide and one of these is not. And so if you just make it a hydroxide, you can now crash out or precipitate out your magnesium hydroxide, leaving your calcium in solution. The last thing you can do is then just react your calcium with carbonate. And if you add the carbonate, then you form a calcium carbonate in solution. Okay, so so that's what's going on. I realized in the other video that I showed earlier, you probably didn't hear anything, so I probably won't go back and re-record, but as they're going through the different metals, they're going from lithium to sodium to potassium to cesium, and when they add the cesium, that's when the whole thing breaks. So that's the one that's most reactive. So ways to distinguish and separate the cations is thinking about sulfates and carbonates and hydroxides, and then the different solubilities at different pH and a different temperature. So here is a question that you should think about. If you add powdered limestone to a lake affected by acid rain, this can decrease the availability of phosphate ion, which is an important nutrient, but not that of nitrate, another nutrient. What would be the balanced chemical equation to justify your answer as to why this is true? So let's think about that for a minute. So we've got acid rain, and we've got phosphate, and we've got nitrate. So I'm going to annotate this a little bit. So if I have CaCO3 and I have some sort of acid in solution, right, then what I'm going to form is HCO3 minus and calcium 2 plus, and then this HCO3 minus is going to react with another H plus to form H2, CO3, which then breaks up into water and CO2. So that increases my calcium 2 plus ion concentration in water. So calcium carbonate in water by itself is not soluble, but calcium carbonate, limestone, will react with acid to break up because you're forming that carbonic acid, and then the thermodynamic preference is favored to drive off that gas, right? Like that's entropically favored and thermodynamically favored. So now if I have calcium 2 plus, and I have some phosphate ion, and I have some calcium 2 plus, and I have some nitrate anion, what is going to happen? Well, this is going to be soluble because all nitrate ions are soluble. But this is going to react to form Ca3PO4 2, which is going to be a solid, right? And therefore, that's going to decrease the availability of the phosphate ion, because now I'm forming a precipitate of the calcium phosphate. So that's what's happening in terms of like limestone being added to an acidic lake. Oops. Okay, so for the alkaline earth metals, except beryllium, which will have the most insoluble hydroxide and the most insoluble sulfate. So magnesium, both magnesium and then barium, respectively, calcium and then magnesium, strontium, or magnesium and then strontium. So we talked about the most insoluble hydroxide, and the most insoluble hydroxide was magnesium. We didn't really talk about why. The magnesium hydroxide is really small. So when you think about lattice energies and lattice enthalpies, the smaller the distance between the two anion and cation pair, then the stronger the Coulombic force, right? And so the magnesium hydroxide was the most insoluble hydroxide. So that takes us down to A, B, and E. And so which is the most insoluble sulfate? So so what you have to remember is that the sulfates is opposite the trend of the hydrogens, of the hydroxides. And so it's either going to be B or E, and the difference between B and E is just where is barium versus strontium, and the answer is B. So the barium sulfate will be the most insoluble sulfate. And again, this is because you have kind of this interaction between the barium and the sulfate, where sulfate is actually quite large and polarizable, and barium is quite large and polarizable. And so there's a covalent aspect to the ionic lattice, and so it's going to be more insoluble because the intermolecular forces between those two large polarizable anions and cations is stronger than the hydration enthalpy of a barium hydrated in water and a sulfate hydrated in water. So because those are so large with small waters associated with them, it's going to be insoluble at the end of the day. Okay, so then finally we get to halogens. And so in terms of halogens, you again have smooth trends in melting and boiling points, whereas I go down the periodic table, my intermolecular forces increase, and therefore my boiling points also increase. It's harder to break up those intermolecular forces. Covalent halides, basically you can just take some non-metallic element and add a halide gas to it, and you form the covalent halide. So phosphorus plus chlorine, you can form the phosphorus pentachloride or the phosphorus trichloride, just based on Le Chatelier, like how much chloride am I putting in there to drive it towards the fully 5-coordinate phosphorus or just the 3-coordinate phosphorus. And so that's true of like nitrogen, that's true of silicon, etc. So fluorine is going to behave differently from all the rest of these halogens because there's a weaker fluorine-fluorine bond. And so most fluorine salts are going to be insoluble. Fluorine compounds are going to have lower melting points and boiling points than chlorine and are going to be more stable. Fluorine causes higher oxidation states than other halides. So it's kind of a weird halide in terms of kind of the family reactivity. So why would HF acid be a weak acid, whereas all the binary acids of the other halogens are all strong? And that again has to do with the strength of the bond between hydrogen and fluorine. F minus is actually a pretty strong conjugate base, and therefore it's going to go back in the opposite way to reform that HF, whereas all of the other halogens have conjugate bases that are quite weak, and so the reverse reaction of a hydrolysis of the acid is just going to lead to acidic conditions. Okay, so synthesis of ionic halides, most of these are soluble. So again, if you just take any metal and you react it with some stoichiometric coefficient of a halide gas, you end up with that metal halide, right? So if I wanted to take what's a favorite metal? If I wanted to take chromium, and I want to take chromium and bromine, so Cr solid, and then 2 bromine 2. This gives you chromium Br3 if that ends up being like chromium in the 3+ state or whatever. So so you need to just add as many halides as you have to match the oxidation state of the metal. and you don't need to worry too much about like guessing if you have the oxidation state right. So then the other way to do it is if I take chromium and I react it with HBr, then I can still get to my chromium Br3 plus hydrogen gas. So that's the other way to do it. And so you're just kind of synthesizing these halides by introducing the halide gas or the hydrohalide acid. So then let's talk about separations again. So here are the chloride solubility constants for these three metals, and here's a complex of these. And so if I had a solution of silver, mercury, and lead, how would I separate these in terms of thinking about insoluble chlorides? So again, we're gonna pop over to the Descriptive Inorganic Chemistry lab. I didn't realize it showed you all the stuff that I watch. So, so here you can kind of just look at the flame test. That's not very exciting. Oh, wait, we have the wrong video. Hold on. Wrong video. Let me get the right videos. Chlorides. Oh no, this is the right one. Okay. Sorry guys. Wah, wah. Okay. So we've got sodium, mercury, and lead in solution. These are basically the only ones that form chlorides. So as we add chlorides, you get them all together. So you can separate, you know, alkali metals from the alkaline earths if you have these three specific ones by forming chlorides. So anyway, so we're just going to put those into solution. So if you think about the lead chloride solubility constant, it's 10 to the negative 5, and the others are 10 to the negative 9, 10 to the negative 10. And so if you just heat it, the lead chloride will go back into solution, so it will dissolve back again. And therefore, you can get the lead out by centrifuging it out. So you kind of remove or decant that solid, and then as it cools, it actually will reprecipitate out. There it is. So there's the lead chloride again. Okay, so now I've got silver and mercury in solution. And so the way to distinguish between those two is that you can add in ammonia. So this goes back to formation constants, which we talked about in the solubility chapter. So I think it was like J, it was 6J, so if you think about complexation. So the silver is much more likely going to form a complex than the mercury, and so you can get it back into solution with that formation constant. What we didn't tell you is that by adding ammonia, you actually do kind of a redox disproportionation of mercury, where mercury is oxidized and reduced to form two solids, one which is the mercury solid and the other which is like a mercury ammonium solid. And so in those cases, that's what happened, but either way, you get the mercury back out. So that's the disproportionation, reduced and oxidized. And then the silver, you can just acidify it again. That takes you back to your chloride formation, and that takes you back out. So, and that works because you have basically, you've basically, where am I? Changed the ammonium to You've changed the ammonium back up to the ammonium chloride, and therefore it isn't available to complex anymore. So ammonia is only going to complex with silver if you're in a basic solution. If you're in an acidic solution, your ammonia can't complex with the silver because it's already in an ammonium cation state, and a cation and a cation are not going to complex together. The only way it's going to complex is if you have a Lewis base component to it, and that Lewis base is not available unless it's deprotonated. Okay, so these are the problems associated with this first section in your homework, or at least there might be some of them. So you should be able to explain the trends and melting point for the alkaline earth metals and the halogens. You should be able to determine what the formulas of the highest oxidation states of the oxides of chlorine and manganese are, and what other oxides of the two elements might resemble each other. You should be able to suggest a possible reason why sodium hydroxide is much more water soluble than sodium chloride. So I didn't tell you that answer, but that has something to do with intermolecular forces. You should be able to deduce the oxidation number for oxygen and hypofluoric acid. You should be able to prepare chromium and chromium 3 and chromium 2 chlorides from chromium metal in a halide reagent and write out those reactions. And then you can remember back to fluoride and how that might affect the composition of teeth in terms of thinking about calcium fluorides and hydroxyapatites. So that is the lecture for the first unit of descriptive inorganic chemistry, and we will get to the next part later. Thanks for tuning in. Hopefully you are all feeling well, and I will talk to many of you soon. Okay, thanks.